Capillarity. Capillarity. The rise or fall of a liquid. The rise or fall of a liquid in a capillary tube. In a capillary tube, when it is dipped in a liquid, is called capillarity. We notice that this capillarity depends on adhesive forces and cohesive forces. When a glass rod is dipped in water, we notice the water column rises inside the capillary tube. So, in general, if angle of contact theta is less than 90, then the liquid rises. For example, water in a glass tube. If angle of contact theta is greater than 90 degrees, then the liquid falls. Example is a glass tube dipped in mercury. If the height of the liquid column is say h, if the height of the liquid column inside the capillary tube is say h, and this is when the capillary tube is dipped vertically. If the capillary tube is kept in an inclined position, making an angle theta with the vertical, if the water column rises through a height L, spreads over a height L, then h will be equal to L cos theta. The vertical height h will be equal to L cos theta. Let us derive a relation for surface tension using capillary rise method. Suppose the capillary rise is represented by this figure. The curved surface, concave curved surface represents the surface of the liquid. Then the surface tension forces act along the tangent, making an angle theta inside the liquid. So the angle theta represents the angle made by the surface tension forces along with the surface of the capillary tube. This force is present along the surface of the liquid in all directions. It is tangential to this curved surface. Then at each and every point, it is resolved into two components, horizontal component and vertical component. The vertical arrows represent vertical components. The horizontal components at the sides represent the horizontal components. Like this, we notice vertical and horizontal components. The horizontal components get cancelled because for each component there exists a component in the opposite direction. For each component on one direction, there exists an equal component in the opposite direction. Hence, the resultant of all these components will be 0. So, there will be a net vertical component acting on the surface of the liquid. There will be a net vertical component acting over the surface of the liquid. We know that surface tension is force per unit length. The circumference of this circle, the circumference of the circular cross section is 2 pi r. Hence, the total force applied by this surface tension in the upward direction is 2 pi r t cos theta. The force acting over unit length is t cos theta. So, over a length of 2 pi r, the force is 2 pi r t cos theta. This balances the weight of the raised liquid column. If m is the mass of the liquid raised, mg is weight. Hence, 2 pi r t cos theta is equal to mg. Here, the symbols indicate T represents surface tension, R represents the radius of the capillary tube, theta is angle of contact, and the height of water up to the lower meniscus is h. Force due to surface tension is 2 pi r into t cos theta. T is surface tension, R is radius of capillary tube, theta is angle of contact, height of water up to lower meniscus is h. Force due to surface tension is 2 pi r into t cos theta. Weight of raised column of water. Is equal to mass into acceleration due to gravity, mg. But mass is equal to volume into density. Hence, the weight is equal to volume into density into G. Volume is pi r h, pi r square h. Pi r square is area of cross section, h is height of the water column. So, volume is pi r square h, and d is density of water, d is density of the liquid, raised liquid, and g is acceleration due to gravity. This is the weight of the liquid. This weight acts in the vertically downward direction. The force due to surface tension acts in the upward direction and the weight acts in the downward direction. They are balanced. The force due to surface tension 2 pi r into t cos theta, it acts in the upward direction, and the weight pi r square h dg acts in the downward direction. When the surface of the liquid in the capillary tube is at rest, then it is in equilibrium state under the action of these two forces. It is in equilibrium state under the action of these two forces. So, their magnitudes are equal. So, 2 pi r into t cos theta is equal to pi r square h dg, from which we will get t is equal to h r dz by 2 cos theta. T is equal to h r dz by 2 cos theta. Here, we have neglected the mass of the liquid inside the meniscus. By neglecting the mass of the liquid inside the meniscus, we will get the relation T is equal to h r dz by 2 cos theta. If we consider the liquid inside the meniscus, we can calculate the weight of the liquid column like this. Volume of the liquid inside the meniscus is equal to volume of a cylinder of radius r and height r, volume of a cylinder of radius r and height r minus volume of hemisphere of radius r minus volume of hemisphere of radius r. Mathematically, pi r cube is volume of the cylinder of height r and radius r. 2 by 3 pi r cube is volume of hemispherical part. So, the volume of the liquid inside the meniscus is pi r cube minus 2 by 3 pi r cube. Pi r cube minus 2 by 3 pi r cube, which is equal to 1 by 3 pi r cube. So, the total volume of the raised liquid, that is up to the lower meniscus is pi r square h. Pi r square h is up to the lower meniscus. Inside the meniscus, it is 1 by 3 pi r cube. Hence, the total volume is pi r square h plus 1 by 3 pi r cube. Pi r square h plus 1 by 3 pi r cube, which is equal to pi r square into h plus r by 3. The weight of this liquid column is equal to pi r square into h plus r by 3 into dg into d into g. Pi r square into h plus r by 3 into d into g. Now, 2 pi r into t cos theta is force due to surface tension. This will be equal to pi r square into h plus r by 3 into d into g. Pi r square into h plus r by 3 into dg. From this, we will get t is equal to r dg into h plus r by 3. R dg into h plus r by 3 whole divided by 2 cos theta. For pure water, theta is equal to 0. Hence, T is equal to half R dg into h plus r by 3. This is the relation for finding surface tension with capillary rays.